Okay, so in this problem, we're still looking for slope and displacement at certain points, but let's see what we've got. We want the slope at A, which is here, and we want the displacement at the midspan, which is here. So when we could do this a couple ways. This is a continuous problem. In fact, we worked this with direct integration. You might remember a couple days ago, or a couple classes ago, we did this. So I wanted to show you in conjugate beam that you could also pull this off, but I wanted to show you kind of the advantages and disadvantages. Now remember, if we did direct integration on this problem, we would have a continuous equation for shear and moment for displacement and slope, and you would have to find where the slope was 0 to identify where the displacement was max. Not hard to do. So let's see what would happen if you decided, now that you have this conjugate beam technique, how to do that. So the first thing we have to do is what? Draw the shear and moment diagram for this. So just like we've done before, I'll assume positive shear at A, positive shear at B. Also, thinking ahead, a little bit of planning, I'm going to want the slope at A, so that means I'm going to want the reaction of the conjugate beam at A. So when I cut the beam here in the middle, I'm probably going to want to work the left side because I'm going to need that slope at A anyway. You're probably not going to find the slope at A and then work the right side. So I'm going to kind of be looking this way when I do my section. Also right there in the middle is where my equivalent load is going to be. So my concentrated equivalent of this distributed load it's a rectangle, so it's going to be base times height. So that'll be WL. And it'll be right in the middle, which will be L over 2. So that should be all I need. In fact, you probably wouldn't even need to do the equilibrium equations to know the reactions, but I'll go ahead and do it anyway to let you see. So if we do some moments at B and make sure it's in equilibrium, about B, this load creates positive moment. So the load is WL and the distance is L over 2. And then I have my shear at A, which creates negative moment times the length of L. So you can see that the shear at A is going to be WL over 2. And then if you sum forces in the y direction, you should be able to find the shear at B. So I'm assuming up is positive, so I have my shear at A is positive. My shear at B is down, so that would be negative. My load is down, that would also be negative. So plug in your shear at A here, you'll find the shear at B is minus WL over 2. So with those two values, I can draw my shear diagram and then use my shear diagram to draw my moment diagram. So let's see what we get. So I'll put some edges of my template. I'll establish my positive x-axis, my positive shear. The units won't matter. We're doing it dimensionless. So what's the shear at A? Positive WL over 2. What's the shear at B? Negative WL over 2. Let's see if that's going to work. So I know the change in shear between these 2 points is the area and the load. The load is WL minus, so WL over 2 minus WL, that works. And what's the slope? Well, the slope of the shear diagram is the value of the load. The load is constant and negative, and you get a shear diagram that looks something like that. So there is a point where the shear is 0. We'll indicate that in our template. And we're going to use that to help us draw our moment diagram. So positive x, positive moment. Oh, first of all, what's this distance here? Well, you can see these are similar triangles. They both have the same height, so they should have the same base dimension. So you got two things that are equal that add up to L. They're each going to be L over 2. So with that information, I can find the area under this part of my shear diagram. It's a triangle 1/2 base times height. So it looks like it's WL squared over 8. So that's my change. And then, of course, the change from the midpoint down is minus WL squared over 8, and that brings us back to 0. So everything is good. Now, what's the shape of the moment diagram? Well, the shape of the moment diagram is given by the shear. The shear starts off positive and decreases to 0. So here's a positive slope, and then here's 0 slope. So we get a parabolic section, looks something like that. And then, of course, the right section starts with a shear value of 0 and goes to a negative value. So there's 0 to negative, and you kind of qualitatively sketch that in. You get your moment diagram. Now you're probably thinking ahead, oh no, I've got to apply a parabolic load to my conjugate beam. How am I going to find the area under my parabolic curve? Well, you could write an equation for it, integrate it. You can do it that way, but you can see where the method starts to break down a little bit. Because now you're working with areas that are not easily computed, not like rectangles and triangles. So that could be a disadvantage. But let's see if we can soldier ahead and get it anyway. I think we can. So what's my conjugate beam look like? I'll try to do a little better with my space management now. So, my external pin stays a pin. My external roller stays a roller. So there's a pin. And there's a roller. And on that, I'm going to pick up this moment diagram and plop it right on there. So it's going to look something like this. It's all positive moments, so this will be positive load. And you'll get a load that looks something like this. And what's the intensity of that load going to be? It's going to be the moment divided by EI. So that's going to be WL squared over 8 EI. Okay? Now that we have our conjugate beam established, what's the problem? Well, we want to find the slope at A. Well, the slope in the real beam is the shear in the conjugate beam. So if I assume positive shear at A, which I will, and positive shear at B, and if I can find the shear at A in the conjugate beam, I have found the slope at A in the real beam. I think that's very doable. What about the displacement at the midpoint? Well, that would be the, and I'll draw a little line here. Let me pick a different color. So if I just were to cut the section here in the center, I need to find the moment here. So if I have the reaction at A, all I have to deal with is this part of the curve. And this part of the curve is okay because that's just a parabolic section. And we know the area of a parabolic section. It's 2/3 base times height. I don't know the centroid off the top of my head, so I'd have to look that up. So we can solve this problem, but I probably don't expect you to be able to pull it off in the exam, because I'm not going to have you memorize general areas and centroids for parabolic or in-order sections. I think that might be a little too much for this course. So you can see this is where this technique starts to break down a bit. But let's see what we can do with it before we run into a problem. So let me redraw this beam, and just with the concentrated equivalent on it. So we still have shear at A, shear at B, and now I'm going to come up with the concentrated equivalent. Now, since this is a nice symmetric parabolic section, I know the centroid is right in the middle, and really the area of this beam, area of this thing, is 2/3 the base times the height. So 2/3 base, which is L, times height, which is all that. I'll just write this as F1, and I'll come up here and solve for F1 as 2/3 the base, which is L, times the height, which is WL squared over 8EI, which is what? Let's see, that becomes WL cubed. Let's see, that's 24, 2, that's 12? And of course the distance is L over 2. So I can find the shear at A. Right? If I sum moments about B, what do I get? Well, about B, with right-hand rule as my sign convention, the force at 1 is negative. So that'd be negative WL cubed over 12EI. That's the force times a moment arm of L over 2. The moment about B for the shear at A is also negative, and that's a length of L. So it looks like the shear at A is going to be negative WL cubed over 24EI. Now remember, the shear in the conjugate beam is the slope. So this tells us what the slope is for that beam.
So it depends on that F1, is that 2/3?
Yeah, that's my 3 got a little wiggly there, but it's 2/3. And if you slide in the book and you look at our problem and you zoom in just for a second, you can see the slope is WL cubed over 24EI. So we got that part right. We also know what the maximum displacement is in the center. I don't know if we'll be able to get that one. Oh, we got to zoom out a little bit here. Okay. Let's see what we'd be up against if we tried to solve the rest of the problem. So I'm going to have to now cut the structure here and look at the left-hand side. So my free body diagram for the cut section would look something like this. So this would be L over 2. I've just found my shear. It's negative. I assumed it was up, so it means it's down. And that's WL cubed over 24EI. Here's my positive shear and positive bending moment at the middle. I don't want the slope at the middle, though. I just want the displacement. So I'm only concerned about the moment. And then my load looks something like this. It's a nice parabolic shape. Now we know from our previous discussion that the area of a parabolic section is 2/3 base times height. That's cool. But I don't know where the centroid is. That's where it kind of goes, I don't know how to solve this problem. So I can find this force. I'll call it F2. So I know what F2 is going to be. It's going to be 2/3 the base, which is L over 2, times the height, which is WL squared over 8EI. Let's see, the 2's cancel, and I get WL cubed over 24EI. And that makes sense, because when I did the whole structure, I got WL cubed over 12EI, so this is half that. That's good. But I don't know this distance off the top of my head. Do any of you guys know that? I don't. So this is where I would have a problem. Now, if you're at home and you have access to your book, you can find these things. Here's the section we're talking about, right? The semi-parabolic section. That's where I get the 2/3 base times height for the area. You can see the centroid is what? 3/8 of the base. I don't know that. I didn't know that till I read it. So I wouldn't expect you to know it either. But if I did want to finish this problem, I would know that this D2 would be 3/8 of L over 2. Three-eighths of L over 2, which you can see is a very strange 3L over 16. So now it wouldn't be hard to do. Some moments I've got force times distance, I can find the middle. But this is where it really, I would have to stop, because on an exam I couldn't do this problem. So that's the sort of thing I want you to think about. If in hindsight now, if I kind of block all this out, let's do it this way. If I block all this out and kind of go backwards to the original problem, and you're thinking, what method should I use? Should you use conjugate beam? Probably not. So what would be your other choice right now? Direct integration. So this is kind of one of those things where it's a slightly negative result, but I wanted to plow through as best we could, and this is kind of where we run into a problem right here. I wouldn't expect you to know that off the top of your head. Now, if as part of the exam I were to give you this sheet, then you would have the tools you need. Hint, hint, nudge, nudge, wink, wink. Okay? So we'll just stop. Any questions before we get past this?